Hello, everyone. So welcome to this first class, and so I guess everybody is having a stress time, and so here it is me. I'm trying to experiment with these things. Yeah, I don't know. I have never been very comfortable with this online teaching, but I guess everybody has to get used to the technological stuff. And so here I'm trying to record my sort of a test class or a test testing of this thing. So what I'm going to do is uh, so we'll not initially try with the online thing, and what I'll do is I'll just give you a set of notes, and also I'll try to record some of the things which are in the notes and try explaining them verbally. So in case when you are having difficulty in reading the notes, you can listen to the voice or the explanation. And in case you don't find the explanation in my voice also, you're free to mail me at any time. And I hope you are firstly doing well health-wise, and everything is going fine. So I just want to continue. So last class we couldn't finish, and then this dreaded thing started happening. And so mm, what we are going to do is we shall try to let me put this on a full screen mode. So what we are trying to do is we are trying to look into the simple random walk, and which has IID increments and has mean 0 and variance 1. And we are looking at the number of points which are positive, and we divide it by n. Then we want to show that let us consider the simple case that they are simple symmetric random walk taking plus minus 1 values. We want to show that they converge weakly to the integral of 0 1 of the Brownian motion, the points where the Brownian motion is positive. So this is simply the Lebesgue measure of the Brownian motion, the points where the Brownian motion is positive. And we want to show specifically that this limiting random variable has an arc sine law. So the arc sine law, the density of the arc sine law looks like this. It's square root of s 1 minus s whenever a is between 0 and 1, or it's otherwise it's 0. So I just want to point out the proof is very technical, and it will require some facts from the Brownian motion which are not in your syllabus, at least for my course. Many of you are doing the Brownian motion course separately. They should be able to follow more, but I would just want to indicate where does this arc sine law come from. And you can take these facts as I say it. So there are many books in Brownian motions which are available, and now you can find these facts on those books. So let us start and see. So last day we saw that there is this beautiful lemma called the Richard's lemma. So I'm trying to repeat what the statement is. So on the left hand side, or at least on my left hand side, you see there is a number of k's. You're counting the number of k's for which the random walk is strictly positive. And we showed that this is exactly equal to the first time the random walk actually achieves the maxima. So there might be multiple maxima in the random walk, but it's you take the first time when it achieves this maximum. So this is what is called the Richard's lemma, and we showed this by a beautiful algorithm by taking by arranging the indices in the decreasing order if SKs are positive, and if it's not positive, then we arranged it in an increasing order and reordered these increments in a different way, and then got this result. So it's a sort of beautiful result which explores an exchangeability property of these random variables. So we are now trying to see whether on this identity on the left hand side. So on the left hand side, as I point my cursor, we will want to apply the continuous mapping theorem. On the right hand side, we also want to apply the continuous mapping theorem and get a result for the previous exercises. So let us see what happens on the right hand side first. The minimum of k's such that sk is maximum of sg's. So the functional we have to take is very clear what we must take. So recall, let xn star be the interpolated random walk. So this is so we take the random walk, we do a linear interpolation, and we call it an xn star. So xn star is the random walk trajectory we have. Now we consider a map T from C01 to 01, which is given by, so you take a function f from C01. So this is given by infimum of T in 01, says that ft is supremum of fs s in 01. So this is again the sort of the first time the function achieves its supremum. Now question is whether this functional from C01 to 01 is a continuous functional or not. It turns out it's not a continuous functional. It's an exercise for you to look for counter examples. But if the function achieves a unique maxima, so if there is a unique point where this fs is achieving the maxima, then definitely this is a continuous functional, because as you can see, there will be a point where this will be achieved, and then the infimum will be achieved, and you can just show that this is continuous. Now, the interesting part is that although this is not continuous, but this is continuous, the set of discontinuity points will have, of this functional, will have zero measure with respect to the minor measure. So I'm just repeating what I said. So if you look at the discontinuity points of T, then it will have zero probability with respect to the Wiener measure. Now, why is this true? This is true, again, as I said, I'll be using some facts from the Brownian motion. This is a fact from the Brownian motion. So which says, forget about these rational numbers. So if you look at, if there are 2 points where the supremum is achieved, then the probability of that happening, so there are 2 points where the Brownian motion behaves same, is 0. So if you locally look at into the Brownian motion, all the extreme points are almost surely distinct. Now this you have to keep in mind when you visualize this picture, that that there won't be 2 points where your maximum will be same in a Brownian motion. Now this is helping a lot. So what we'll do is we'll apply this T map on xn star. So let us look into what happens if we apply T on xn star. So T on xn star is the infimum of all the T's, such that xn star T is the supremum of xn star S. Now note that xn star T is a linear interpolation. So so there will be points where so it's a piecewise linear functional. So it will achieve the supremum only on the points which has the cliques. So as you can understand, so you can just evaluate it at discrete points. Otherwise, it's a linear functional. So what happens is, now x and t, you can just discretize it and make it sk by n. And this side is xn star. As you can see, it will be sj sj by root n, maximum of this. And this minimum of k in 0 to 1, you can think of it's like minimum of k by n. So when you're taking the infimum between 0 and 1, you will be taking instead infimum at 0, 1 by n, 2 by n, 3 by n, like that. So that's why this 1 by n scaling comes out. And you can always cancel out these root n's there, and then you will land up on the right hand side of the Richard's lemma. So that's what you have. Now if you apply the continuous mapping theorem, because you can apply that, the general continuous mapping theorem, because the Wiener measure makes it almost surely continuous. So hence what you get is T of xn star would converge to T of w. Now the problem would be like how to identify T of w. This will require some facts from Brownian motion again. So let us look into it. So what do we want to do? So what is T of W? T of W is an M. It's a M minimum of M, all M such that Wm is the supremum of Ws. So where S is between 0 and 1. And note that such a M will be well defined. So because you have this local, the fact I said that this locally you cannot have a suprema same in 2 points. So what happens is if you, now let us denote by MT the supremum of the Brownian motion from 0 to t. So this is the moving maximum. Now when you look at, let us look at M less than equal to S. So what are you doing? So if you see what is M, M is the point where the supremum of the Brownian motion has been achieved. So what does it mean? This supremum is less than S. This point is less than S, means that the maximum between 0 to S has already happened, and it's more than what happens later. So it's the total maxima. The total maxima is more than what is happening after S and 1. So this is between S and 1. So this is more than S and 1. In the next step, what you do is you subtract a WS from both sides. And now what you do is you change a variable. So what you do is you change this, say for example, this side, when MV minus WS, what you do is you denote V by say some U plus S. Then you do a change of variable and make it, so what are the M1 and M2s? M1 and M2s is the maximum of W1U, where W1U is just a shifted process. So WS minus U, so W is the Brownian motion, WS minus U minus WS. And M2 is also a maximum of a shifted process, where the M2 is the moving maximum of WS plus U minus WS. Now, if you calculate the covariance structure of W1 and W2, you can show that they are again a Brownian motion. So what you get, if you go back to this quantity, you can easily show, for example, that from this line, it requires pen and paper. You should take a pen and paper and write down. So this is M1S greater than M2 1 minus S. Very good. And both are maximums of Brownian motion again. One is up till S and another is 1 minus S. Now what you do is you use this fact. Again, I'm using a fact that MT is modulus of WT. So you remember in the class already I showed that M1, for example, the maxima from 0 to 1 is mod of W1, which is a mod of a normal random variable. But this is true much more generally, that MT is in distribution same as WT. Now let us see what interesting thing happens. Suppose you take two random variables Z1 and Z2, which are independent normals. Now you want to calculate this probability that M1S is greater than M2 1 minus S. What is this? By this fact, you can write this as W1S mod of W2 1 minus S. So this is a normal random variable with variance S, and this is a normal random variable with variance 1 minus S. You just write it in this form, that square root of S into mod of Z1 greater than square root of 1 minus S into mod of Z2. Now you square both sides and do a manipulation, and you can show that this is nothing but Z1 mod Z2 by Z1 square plus Z2 square less than root S. So what you have is, so you have to find out what this distribution is. How to find out that? So what you do is you jointly see Z1 and Z2. It's a two-dimensional vector now. You write it as a polar coordinate, r cosine theta, r sine theta. And you can write down from the joint densities. It turns out very easily. So what does the joint density of Z1 and Z2 look like? It's the integral, it's a double integral e power minus x square plus y square dx dy. So what happens is, what happens to this angle in the polar coordinate? The angle immediately becomes uniform 0 to 2 pi. So it's a nice thing for us. So whenever you write z2 by z1 square by z2 square, in terms of polar coordinates, this is nothing but the sine theta. So this is what sine theta of less than square root of x. So then you do a bit of juggling around with the theta function. What you get exactly is theta less than sine inverse of or arc sine of root s, and you get the density. So this is how I wanted to point out that the arc sine law comes. Now we have done this for only for the if we go back to the Richard's lemma. So what we did was we looked at this side of the equation. Now let us look at the number of points where Sk is positive. So this is also a bit on the trickier side. So let's look at the functional will be. So what we showed here is the number of points k such that Sk is maximum of Sj divided by square root. Oh, this is a typo again. So this is if you divide by n, it converges to the arc sine law. Very good. So define the map H from C01 to 01. Where HF is integral 0 to 1, indicator of Fs greater than 0. So you're looking at the points of the Lebesgue measure of the points which are positive. Now again the question is whether this functional is a continuous functional or not. So the answer is no. So now what you want to okay, so before coming to this whether this is a continuous functional, we want to see what happens if you apply it on h of xn star. So note that if you apply it on h of xn star is the linear interpolations of the random walk. So what you have is you're looking at what are the points in the interpolated random walk which are positive between 0 and 1. So what you can find out is, this is not difficult to find out because what you're doing is you're already centering this xn star. So xn star, remember, is the centered one. So this is mean 0, variance 1 kind of variable. So this is the centered one. So what you can do, you can show that if you apply this, there is an approximation error in the sense that how far is this from the left-hand side of the Richard's lemma. So if you so we find that the difference is of the order of you have to find out the number of k such that Sk is 0 in the simple symmetric random walk, and this goes to 0. And this fact can be checked from the if you just do an estimate from the random walk, that the probability of the points where this is 0 is of the order of root n. So if you divide this by n, you would go to 0. So you can use a Markov inequality and show that this quantity goes to 0 in probability, and hence you are almost approximating the correct thing. Now suppose H is not H is not continuous on C01, but it is continuous around 0. So if you remove the properties around 0, so if it has Lebesgue measure 0, then it is continuous. So for example, if your functions satisfy this property that 0 to 1 indicator of ft 0 to epsilon dt as epsilon goes to 0, this is 0. If you push in the epsilon inside, this is equivalently, you can show that this is the set of points ft which are 0. So the Lebesgue measure of the points where the function is 0 is 0. So this is continuous for all these functions. And it is again a fact that the Brownian motion satisfies this. So what does it mean? So if you look at the 0 set of the Brownian motion, so the set of t's where bt is 0, this has Lebesgue measure 0. This is again a fact from Brownian motion. Now, so what it shows now, if you apply this functional, what on the side of with xn star, what you get is the number of points where Sk is strictly positive divided by n would converge to this function. Now, by uniqueness of the limit, what you will get is that you have the arc sine law. Okay, so there I'm using a lot of stuff from Brownian motion, but this is just to give you an idea from where this strangely appearing arc sine law comes. Uh, uh, if you have any queries or any doubts, you're free to ask me. Uh, but I would advise you to try and write this proof down. The lecture notes are with you. And okay, so next what we are going to do is we'll start off with D01 very soon. I'll send you a link for that also.